The present study simulates the heat transfer of water flow through a zigzag channel. The zigzag channel shape is one of the most widely used because of the relatively simple manufacturing process and low cost. However, the heat transfer enhancement of a zigzag channel is at the expense of increasing the pressure drop. The present 2D model is drawn using Design Modeler software. The present model is related to a channel that has a zigzag structure in its horizontal direction. The number of these zigzag modes is 10. In one model, the channel angle is 15 degrees relative to the horizontal ridge, and in the other model, 45 degrees. The figure here shows the graphic geometry for both modeling modes, a 15-degree and a 45-degree angle. The meshing has been done using ANSYS meshing software. The mesh type is structured and the element number is 48,000, and the following figure here shows a view of the mesh. To simulate the present model, several assumptions are considered, which are: the solver is pressure-based due to the incompressibility, the simulation is steady, and the gravity effect is ignored. Turn on the energy equation to compute the temperature change in the simulation. In this case, due to the low velocity of the flow and the Reynolds number due to this velocity, the flow is laminar, so enable the laminar model. In this section, you can see the properties of the water liquid. You can change any of these properties by entering the new values. Also, you can choose the material from the Fluent database. Choose the material that you want from the Fluent Fluid materials, and then click on the copy. In this dialog box, for the fluid zone, set the water liquid material and then click on the apply. In the operation conditions tab, you can set the operating pressure. Set the velocity inlet boundary type for the inlet, and then in its dialog box, enter the value you see here for the velocity magnitude. And in its thermal tab, enter the value for the temperature, and then click on the apply. Set the pressure outlet boundary type for the outlet, and then click on the apply in its dialog box. For the bottom wall, set the wall motion to a stationary wall and no slip for the shear condition. And in the thermal tab for this boundary, set its heat flux to 0 to define this boundary as a insulation. Likewise, for the upper wall, choose the stationary wall for the wall motion and no slip for the shear condition, but in its thermal tab, enter the value you see here for the temperature. We use the simple scheme for pressure velocity coupling. Actually, the simple algorithm uses a relationship between velocity and pressure corrections to enforce mass conservations and to obtain the pressure field. For the discretization, choose the second order for the pressure discretization and second order of wind for both momentum and energy discretization. Now I want to explain you how you can export the values of the desired variable during the solution. In this dialog box, at first select the report type, then select the variable you want, then choose the surfaces to export the values on them, and then enter the name for this report. Also, you can enable the report file to write the exported values in a text file during the solution, and you can also enable the report plot to have the possibility to see the plot in the graphic window during the solution. Then click on the OK. All of these boxes must be disabled because if the remainder of this equation reach the absolute criteria values, the software thinks that the solution converges and stops solving, but we want the solution to continue as long as we want. Then click on the initialize. In this window, you can set the conditions under which your case and data will be saved during the solution. Enter the number you want in the box to store the case and data for each number. Also specify the path to save the files. Here enter the number of iterations, then click on the calculate. The last thing I want to tell you in this section is how to save the case and data whenever you want. You can do it by clicking on the file, write case and data. Open the CFD Post software and then load the results. To have the contour from each variable you want, at first you must click on the contour icon. In details of contour, at first you must choose the locations that you want to have the contour on them, and then select the variable that you want to have the contour of it. For example, here I choose the pressure. Then click on the apply. Double click on the default legend view one from the tree outline, and then in this dialog box you can specify the name for this legend. Also you can select the location and set the location by the values for the legend. Also, you can set the appearance for the legend view in the appearance tab. You can enter the value for the size, change the aspect, and you can change some text parameters such as precision, font and font color, text rotation, and text height. At the end of the speaking in this section, I want to show you how you can export the image from this contour. Click on the camera icon, then in its window, at first specify the path to save the image, and then select the format that you want. Also, you can set the size. You can choose the screen size or specify other size for your picture, and set the image quality, then click on the save. Back to the Fluent software, I want to show you how you can plot the Nusselt number. Follow my cursor. After the solution process is completed, two-dimensional velocity, pressure, and temperature contours are obtained for two modes with angles of 15 and 45 degrees. Also, the Nusselt number on the upper wall of the channel along the length for the two modes with angles of 15 and 45 degrees. As can be seen from the velocity contour, the amount of maximum velocity and the average velocity in the case of an angle of 45 degrees are greater than in the case of angle of 15 degrees. It also reduces the rate of pressure drop. Also, considering the Nusselt number and temperature contours, I can say that the temperature changes are in the case where the angle is larger with a greater gradient than in the case where the angle is 15 degrees and is smoother for the angle of 15 degrees. This table is an overview of the methods used in this simulation. In this table, you can see the models used, boundary conditions, discretizations methods, and initialization. To benefit from MR-CFD services, including simulation, consultation, and training, contact our experts via info@mr-cfd.com, www.mr-cfd.com.